Okay, in this video we are going to cover section 5.2, and that is area. At the beginning of the course, remember, there were two basic problems that led to the development of calculus. One was the tangent line problem, or finding the slope at a given point on a curve, and the other question is the area under a curve, and this is where we start to explore that idea. So in this section we're going to learn about this new sigma notation to write and evaluate summations, understand the concept of area as it applies to calculus. We will approximate the area of a plane region and find the area of a plane region using limits. So this sigma notation. In the preceding section you studied anti-differentiation. In this section you will look further into the problem introduced in section 1.1, finding the area of a region in the plane. At first glance, these two ideas may seem unrelated, but you'll discover in the next section, or in for our book, section 5.4, that they are closely related and by an extremely important theorem called the fundamental theorem of calculus. This section begins by introducing a concise notation for sums. This notation is called sigma notation because it uses the uppercase Greek letter sigma written as, and it looks like this, sort of like a letter E, almost. But that is our sigma notation. So sigma notation, the sum of n terms, a sub 1, a sub 2, a sub 3, all the way up to a sub n, is written as, we have our summation symbol, and then we start with the letter I. I tells us we are beginning at the number 1, and we're going all the way to the nth term. We're summations from I equals 1 to n of our term a sub I. And that just means we're summing up n terms, a sub 1 plus a sub 2 plus a sub 3, all the way up to a sub n, where I is called the index of summation. A sub I is the ith term in the sum, and the upper and lower bounds are n and 1. The lower bound is down here after the letter I. The upper bound is up on top. In this case it's n. Note, the upper and lower bounds must be constant with respect to the index of summation. However, the lower bound does not have to be 1. We do not have to start at 1. Any integer less than or equal to the upper bound is legitimate. So here's a couple examples of this summation. We're summing from I equals 1 to 6 all the terms of I. So that is first term 1 plus the second term 2 plus 3 plus 4 plus 5 plus 6. And if we sum those up, we get 21. In the next example, we do not begin summing at the first term. We begin summing at 0. But the idea is the same. We take our first term, we plug it in for I. 0 plus 1 is 1. For the second term, it'll be term number 1, 1 plus 1 is 2. And then we go 3 plus 4 plus 5 plus 6. So here our upper bound was 1 lower. It went from 6 to 5. And our lower bound went from 1 to 0. And instead of having just plain old I, we had I plus 1. And the summation turns out to be exactly the same, 21. Here we're going to use the letter J instead of I. It really doesn't matter, and we're not starting at 1. The summation from 3 to 7 of all the terms squared. So we start at 3. 3 squared, plus the next term 4 squared, plus 5 squared, plus 6 squared, squared, plus 7 squared. And let's even take some of the numbers out of it, leave it a little more abstract. We have the summation from k equals 1 to n, and then we first have a fraction 1 over n, and then in the parentheses k squared plus 1. Well, if we start at the first term, we're still going to have 1 over n, and then in the parentheses we'll have 1 squared plus 1, 1 squared plus 1, plus the next term would be 1 over n times, instead of 1 squared plus 1, now we're up to 2 squared plus 1. And we'd continue on in that pattern. And then our nth term, 1 over n, times whatever n is, n squared plus 1. And the last one here is going to start to get us into this notation that we'll be using for calculus. F is a function, f of x sub I, and delta x is our change on the x-axis. And we're summing from 1 to n. You know, this is just more calculus notation. So our first term is f of x sub 1 times delta x. Plus our next term would be f of x sub 2 times delta x. Plus, you know, dot, 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 the next terms, all the way up to f of x sub n, whatever our last term is, times delta x. The following properties of summation can be derived using the associative and commutative properties of addition and the distributive properties of addition over multiplication. In the first property, k is just a constant. So here we have the summation from I equals 1 to n of k times a sub I. Well, the k is just a constant, sort of like the constant multiple rule when we are deriving. We can drag that k out front. And then we have k times the summation from 1 to n of a sub I. We would do the summation and then multiply by k. Going back to this first example here, part A, what if that was 2 times I? You know, we could drag the 2 out front, do the summation just like we did here, and then multiply by 2. 2 times 21 would be 42. So k is just a constant, we can bring it out front. And if we have the summation of a sum or a difference, we can break it apart. The sum of the first term, plus or minus, whatever the case may be, the sum of the second term. This next theorem lists some useful formulas for sums of powers. Proofs of these are given in the book in Appendix A. The first one, the summation from 1 to n of some number c. Well, if it's just a constant c, we just multiply c times n. Our upper limit and c times n is the answer. For number 2, the summation from 1 to n of I is n times n plus 1 over 2. And again, let's go back to example 1, part A, and look at this. You know, the summation of a variable is n times n plus 1 over 2. Oops. N times n plus 1 over 2. You know, we wrote out the summation because it wasn't very long. We got the answer of 21. But if we use this formula, we look at our upper limit. Our n was 6. If I plug 6 in right now, I'm going to get 6. In the parentheses, 6 plus 1 is 7, divided by 2. 6 times 7 is 42, divided by 2 is 21. So that saved us all the busy work of writing that all out and adding it all up. We just figure out what our upper limit is for just a variable, we plug it into this formula, and we're good to go. If we have a squared term, the summation of I from 1 to n of something squared, we can plug that upper limit n into here. N times n plus 1 times the quantity 2n plus 1, all divided by 6, will give us the shortcut to the answer. For the third power, summation from I equals 1 to n of I to the third power is, we take our upper limit again, n squared plus, or n squared times the quantity, n plus 1 quantity squared. And then all of that is divided by 4. So those are some helpful summation formulas we'll be referring back to as we work our way through this section. Example 2, evaluating a sum. So it says evaluate the summation from I equals 1 to n of I plus 1 over n squared, and we're going to evaluate that for 4 different quantities. N is 10, n is 100, 1,000, and 10,000. First, let's take what we have here and get it into a little more workable form. So we have our summation from I equals 1 to n over I plus 1 over n squared. Now n is just a number. So by that constant multiple rule, I can pull this n squared denominator out front. And when I pull it out front, remember it is a denominator, so it's going to stay a denominator. 1 over n squared. And then we'll have our summation from I equals 1 to n. Now we don't have the n squared anymore in our denominator. We pulled that out. Now we have I plus 1. So we use sort of that constant multiple rule to pull that out front. Now we have the summation of a sum. So we're still going to have our 1 over n squared. And let's break this apart into 2 separate summations. So we're going to have the summation from I is 1 to n of I plus the summation from I equals 1 to n of 1. And I guess I should have this in brackets or parentheses because we factored out that 1 over n squared, and that would be distributed over, that quantity. Well, now we can go back to the formulas that we saw in the preceding slide and figure some other stuff out here. So I'm going to hop up this way. We still have our 1 over n squared out front. Well, let's see. The summation from 1 to n of something I, if we go back to that formula page right here, we have our answer. N times the quantity n plus 1 over 2. So I'm going to replace that first summation with n times quantity n plus 1 over 2 plus our next summation from I equals 1 to n of a constant. Remember, that just says we bring the n down and multiply it by the c, whatever that number is, n times c. So here we're going to have n times 1 is n. Now, we could distribute that 1 over n squared right now, but let's get everything inside those brackets into a single quantity. So let's see here. If I distribute the n up top, we're going to get n squared plus n over 2 plus. Well, to combine anything, we're going to need a common denominator. I want to put a 2 under this n. If I multiply the denominator by 2, I have to do the top also by 2. So that becomes 2n over 2. Now it's all under, or it's all got the same denominator. So I can combine all of that. So I'm going to have n squared plus n plus 2 more n is n squared plus 3n all over 4. All over 2. I'm running out of room here. So I could distribute that the n squared in the denominator now, and some stuff will cancel. In our numerator we have n squared plus 3n. Distribute that n squared through the denominator, we have 2n squared. And now you notice every single term has an n. So I can factor one of them out. We have n to the first here, that's our lowest power. That one is completely gone. This one is now knocked down to a first power, as is the denominator, n to the first power. So now we have n plus 3 over 2n. There is our simplified version of how to get to the answer we're looking for. Let me get some of this out of the way here. And now we have our summation all simplified, and we want to evaluate it now at 4 quantities, 10, 100, 1,000, 10,000. And this is going to give us a nice shortcut way to get there. So there's our n plus 3 over 2n. Let's see, if we plug 10 in for n, we're going to have 10 plus 3 is 13. 13 over 2 times 10. So that was 13 over 2 times 10 is 20. And if we reduce that down to a decimal, we're going to get 0.65. If we plug the 100 in, we're going to have 100 plus 3, or 1 over 3, over 200. As a decimal, that's 0.5150. If we plug in the 1,000, we're going to have 1,003 over 2,000, which as a decimal is 0.50150. And then we plug in the 10,000. 10,003 over 20,000. And that decimal is 0.50015. There we go. Now, in the table, note that the sum appears to be approaching a limit as n increases. 0.65, 0.5150, 0.50, 0.500. It does look like we're homing in on a single number. Although the discussion of limits at infinity in a previous section applies to a variable x, where x can be any real number, many of the same results hold true for limits involving the variable n, where n is restricted to positive integer values. So to find the limit of n plus 3 all divided by 2n and n approaches infinity, we can write, the limit is n approaches infinity of our n over n, or n plus 3 over 2n. We break that into separate pieces. N over 2n is our first chunk, 3 over 2n is our second chunk, and then our n's will cancel out. So we're going to have the limit as n goes to infinity of 1 over 2 plus 3 over 2 times n. And now we let the limit be applied. Let n go to infinity. So the 1/2 stays a 1/2. 3 divided by 2 times infinity is 0, and a half plus 0 is a half. In Euclidean geometry, the simplest type of plane region is a rectangle. Although people often say that the formula for the area of a rectangle is a equals base times height, it is actually more proper to say that this is the definition of the area of a rectangle. From this definition, you can develop formulas for the areas of many other plane regions. For example, to determine the area of a triangle, you can form a rectangle whose area is twice that of the triangle. Once you know how to find the area of a triangle, you can determine the area of any polygon by subdividing the polygon into triangular regions, as shown in figure 4.6. If we have a parallelogram, we can draw a diagonal through it, and we've just chopped it into 2 triangles. If we have a hexagon, we can connect opposite angles and chop that up into 6 triangles. Any polygon we can subdivide into smaller triangles. Finding the areas of regions other than polygons is more difficult. The ancient Greeks were able to determine formulas for the areas of some general regions, principally those bounded by conics, by the exhaustion method. The clearest description of this method was given by Archimedes. Essentially, the method is a limiting process in which the area is squeezed between 2 polygons, one inscribed in the region and the other one circumscribed about the region. For instance, in figure 4.7, the area of the circular region is approximated by an n-sided inscribed polygon and an n-sided circumscribed polygon. For each value of n, the area of the inscribed polygon is less than that of the circle, and the area of the circumscribed polygon is greater than the area of the circle. Moreover, as n increases, the area of both polygons become better approximations for the area of a circle. So here in light blue is the circle, and around the outside of it we have a 6-sided polygon. If we find the area of the 6-sided polygon, it's an overestimate because we see there's these white regions that are part of the polygon but outside the circle. So that's an overestimate. We could also inscribe within the circle a 6-sided figure. And we could find the area of that 6-sided figure, and that would be an underestimate because we see there are portions of the circle that are outside that red hexagon that are actually part of the circle. So the blue polygon is an overestimate, the red is an underestimate. And as we increase, this is n equals 6, we have a 6-sided polygon. As we get more and more, here is a 12-sided polygon, circumscribed and inscribed in and about a circle. When you increase the number of divisions, you're going to get closer to the true area of that circle. And there's a picture of my buddy Archimedes. He used this exhaustion method to derive the formulas for areas of ellipses, parabolic segments, and sectors of a spiral. He is considered to be the greatest applied mathematician in all of antiquity. So area of a plane region. If we think back to chapter 2, we know the origins of calculus are connected to 2 classic problems, the tangent line problem and the area problem. Example 3 begins the investigation of the area problem. So, approximating the area of a plane region. Use the 5 rectangles in figure 4.8a and 4.8b to find 2 approximations of the area of the region lying between the graph of negative x squared plus 5 and the x-axis between 0 and 2. So here is our curve, negative x squared plus 5. It's a downward opening parabola, x-intercept or a y-intercept at positive 5. And we're looking on the x-axis between 0 and 2. We want to find out how much area is under that curve, bounded by the y-axis, the x-axis between 0 and 2, and our parabolic curve, negative x squared plus 5. Let's see, and then we're going to do, this will be our underestimate. When we find the area, by finding the area of these light purple rectangles, we'll have an underestimate of the area under that curve. And then next we'll do an overestimate. we'll have our triangles or our rectangles actually go outside of the parabolic curve. So these pieces that are above the curve will be extra. It will be an overestimate. And we know that the true area under that curve will be somewhere between our underestimate and our overestimate. And the first one, our underestimate, we'll do it old school. We'll do it by the formulas that we showed earlier in the video. When we do the overestimate, I'll show you how to punch all this right into the handy TI-89 calculator. And it'll make a little bit more short work out of it. So let's see, our equation was negative x squared plus 5. Negative x squared plus 5. If we look at the picture, to find the height of each rectangle, the width of each rectangle is 2/5. So our delta x, or our width of each rectangle, is 2/5. We've chopped up our area into 5 segments. 1, 2, 3, 4, 5. So we have 5 rectangles that we're using for this estimate. And to find we know that each width is 2/5. That does not change. Every rectangle is 2/5 wide. But how tall is each rectangle? Well, to find a point, to find the height, we would plug 2/5 into our given function, and that would go up. When we hit the curve, we hang a left and we hit the y-axis. So that will be our height. We're going to evaluate the right end of this right end of the rectangle in our function, and that will give us the height. So let's see, we just got to get a couple small things out of the way here. So we need to find our right endpoints. We sort of need a formula to show us where those right endpoints are. And if we look, we have one at 2/5, 4/5, 6/5, 8/5, and 10/5. Well, that means it is 2/5 times I, whatever interval we're on. Here is our first rectangle. 2/5 times 1 is 2/5. Our second endpoint, 2/5 times 2 is 4/5. Our third endpoint, 3 times 2/5 is 6/5. So here are the right endpoints that we will be evaluating in the function. The width I already have up here as 2/5, and our height, the height of each rectangle is f of the right endpoint. End point. So we take the right endpoint, we plug it into our function, and that will give us the height of the rectangle. And this, here I'm just going to show these are sort of our rectangles. From 0 to 2/5 is one rectangle, and then from 2/5 to 4/5, from 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5. And what we're doing is evaluating the right endpoints. Again, when we plug our endpoint into the function, it goes up. We hit the curve and immediately hang a left, and that is our height of the rectangle. So it is an underestimate. We have these little chunks that are above the rectangles but under the curve. We're not counting them, so our number will be a little bit low. So, the sum of the series. So our summation is the summation. Ooh, that's an ugly summation. The summation from I equals 1 to 5. We have 5 rectangles, and we are plugging our endpoints into this equation. So it's going to be negative, and our x values are now our endpoints, 2/5 I, and that x is quantity squared plus 5. So what we have right here is the height of the rectangle, and I'll write it underneath in a different color. This is the height of each rectangle, and of course we're going to multiply that by the width, and the width, or our delta x, was 2/5. So this is our width. And there we go. I guess I can get some of this out of the way now, because we have our summation. That's the important thing. And again, this one we're going to do old school. When we do the overestimates, the left endpoints, we'll just do that on the calculator. So we want to get this into a form that we can use those formulas from earlier in the video. So let's see, this 2/5 is just a constant. We can pull that out front. So we're going to have 2/5 times our summation from I equals 1 to 5. And let's start playing around with the numbers inside here. We're going to have negative, and when we square 2/5 I, 2/5 squared is 4/25 I squared plus 5. Now it's getting, that I squared is something we can plug a formula in for, and we can pull some other stuff out front. So let's see, and I'm going to break this into two separate summations. Remember, the 2/5 will be distributed over everything. And for the first summation, I can factor out this negative 4/25. So we're going to have 2/5, and we factor out the negative 4/25, and then we'll have our summation from I equals 1 to 5 of simply I squared plus, we're going to have 2/5 times the summation from I equals 1 to 5 of 5. From I equals 1 to 5 of 5. Remember, this 2/5 was distributed over everything. So it is here multiplied by the negative 4/25 that I factored out in front of the I squared. And I also need that 2/5 to be distributed across to that 5. So we're moving right along. Okay. So, let's see, should we do anything with this right now? Yeah, why not? If we multiply straight across, we're going to get negative 8 over 125. And then we have our summation. Now, I squared was the same thing as n times the quantity n plus 1 times the quantity 2n plus 1 all over 6. And our n value is 5. So it's n times n plus 1 times 2n plus 1 all over 6 plus 2/5. And then remember, the summation for just a number, we multiply n times the number in front that we're summing. 5 times 5 is 25. And I'm going to put that over 1 because we're going to see some stuff cancel here. I guess I didn't have to break that apart. Right here we can see the 6's will cancel. The 5 into the 125, that'll cancel the 5 out, and this will be reduced down to 25. So let's see what we got here. This 25 and 5 will reduce. That'll reduce down to a 1, and then this will reduce down to a 5. So let's see what we're left with. And when we multiply straight across, we have negative 8 times 11, or negative 88 over 25, plus 10. 2 times 5 is 10, but let's get a common denominator. 10 is the same thing as 250 over 25. And I'm going to have to bust out the calculator here. Okay, I'm just looking, we know our denominator is 25. Our numerator is 250 minus 88. 250 minus 88 is 162 over 25, and that's positive. And 162 divided by 25, let's get this into decimal form. It'll be easier to compare at the end. That is approximately 6.48. Again, that's approximately. So we want the area under the curve. We've used these underestimate rectangles and came up with 6.48 units squared, whatever that is. And we'll refer back to this after we do the overestimate. Again, here are rectangles. When we plugged in our endpoint, our right endpoint, we went up to the curve, hung a left. That was our height on the y-axis. When we do the overestimates, we'll plug in the left endpoint. It might be easier to see over here at 4/5. If we plug in the left endpoint, we go up till we hit the curve, and then we hang a right until we hit the next interval, and that makes our rectangle. So these are going to be taller than the curve, have some area that we're overcounting for this. So, how do we come up with the equation for the left endpoint? Our first endpoint is 0. So we need to come up with our left endpoints. And our left endpoint is 0. Let's see here. If we do our rectangles are each 2/5. 2/5 times I minus 2/5. So for our first interval, for interval number 1, we plug in a 1 and get 2/5 minus 2/5. That's 0. For our second interval, 2/5 times 2 is 4/5 minus 2/5, which is 2/5, our left endpoint. And we'll continue in that fashion. So we have our left endpoints in sort of like a formula. And if we get this all with a single denominator, we already have our common denominator of 5. It's going to be 2i minus 2. So there's our left endpoints. Again, our the width, or our delta x on the x-axis, is still 2/5. So to find the area of the rectangles, it is a summation from I equals 1 to 5 of the height of the rectangle, 2i minus 2 all over 5, times the width of each rectangle, 2/5. And we could plug it in the calculator like this. Still with that constant multiple rule, I do like to drag that 2/5 out front. And then we'll do the summation from I equals 1 to 5 of 2i minus 2 all over 5. So I'm going to copy this. And here on the next slide is how you're going to have to punch it exactly into the TI-89. So the 2/5 is out front. Punch in 2 divided by 5, or you could just do a decimal point 4. The summation symbol is the F3 key, number 4 on the F3 drop-down menu. Be careful with the grouping symbols, the parenthesis. So when you hit the summation, they will give you a left parenthesis. Then you want negative parenthesis, 2x minus 2, divided by 5, close off that parenthesis, and up caret 2, because that's the quantity squared, plus 5. And then we have our comma x, that's the variable. Usually we use I in the book notation, but on the calculator it's just easy to replace everything with an x. So we're telling it we're using the x variable, comma, lower bound 1, comma, upper bound 5. And then you hit the enter key, and I think it gives you directly into decimal form. If it does give it to you in a fraction, it'd be 202/25, which is approximately 8.08. 8.08. And again, what's that telling us is we were trying to find the area under a curve, and we used a left-hand sum, a left endpoint summation of the rectangles, and we know that that definitely is an overestimate. So 8.08 is too big. 8.08. Our underestimate was 6.48. 6.48. So we know that the truth lies somewhere in between. The exact area underneath that curve, negative x squared plus 5, is somewhere between 6.48 and 8.08. We used a very crude estimate with 5 triangles. What if we had did that with cutting each of those in half? What if we had done it with 10 triangles? If we did it with 10 triangles, these overestimates wouldn't quite be so big. And also with the underestimates, if we cut each of these rectangles in half, we would have less of an underestimate. The more rectangles, the better we get. So the procedure used in example 3 can be generalized as follows. Consider a plane region bounded above by the graph of a non-negative continuous function, y equals f of x, as shown in figure 4.9. Do I have figure 4.9? Yeah. So we have an area under a curve. Where were we? The region bounded below by the x-axis and the left and right boundaries of the region are the vertical lines x is a and x is b. So here's x is a is our left boundary, x is b is our right boundary. To approximate the area of the region, begin by subdividing the interval from a to b into n subintervals. Each will have a width of delta x, which is just b minus a divided by n. Sort of like an average. You take your upper bound b, subtract your lower bound a. You want to chop it into subintervals, n of them, so you divide by n, as shown in figure 4.10. So this must be figure 4.10. Again, we're cutting it up into rectangles between A and B. The endpoints of the intervals are as follows. Here's our first endpoint, second, third, all the way till the end. Because f is continuous, the extreme value theorem guarantees the existence of a minimum and maximum values of the function in each subinterval. And for notation, we use f of lowercase m sub I as the minimum value of the function on the ith subinterval, and capital M, f of capital M sub I as the max value of the function on the ith subinterval. Next, define an inscribed rectangle as lying inside the ith subregion, and a circumscribed rectangle as extending outside that ith subregion. The height of the ith inscribed rectangle is f of m sub I, and the height of the ith circumscribed rectangle is f of capital M sub I. For each I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle. So here's our area of the inscribed, the area of the circumscribed, and again the truth is going to lie somewhere in the middle. The sum of the areas of the inscribed is called the lower sum. The sum of the areas circumscribed rectangles create is the upper sum, or the overestimate. And then here's our notation. The lower sum, lowercase s sub n, is the summation from I to n of f of m sub I times delta x. Again, delta x is the width of each rectangle. So that's our inscribed. The upper sum, or overestimate, capital S of n, is the sum from I equals 1 to n of f of capital M sub I delta x. So from figure 411 down here, you can see that the lower sum, lowercase s sub n, is equal than, or is less than or equal to the upper sum, capital S sub n. Moreover, the actual area of the region lies between the sums. Lower sum, upper sum, the actual value is somewhere in the middle. Again, here's our lower sum. We see there's areas that we're not counting. That's an underestimate. Here is the upper sum. We have some areas that extend outside the curve, so this is an overestimate. The true value of the area of the region lies somewhere in between.